Alright, now we're going to talk about acid and base strength. So this is where the English language and Hollywood have really done a lot of damage to chemical understanding. So acid strength does not refer to an acid's ability to burn you or melt your flesh. Instead, what it refers to is something just as simple as dissociation. So dissociation, we've talked about a lot, is just when a molecule, typically ionic compound, breaks apart, dissociates into its individual ions in a solution. So in the case of an acid, a strong acid like we're showing up there, so we're using HA just to represent a general acid. So H being the proton, the H plus, the Arrhenius definition of an acid, and A being some anion, so some minus charged ion. So then what happens is HA is going to donate a proton over to water. That's the Bronsted-Lowry definition, making H3O plus and A minus. What we're saying when we talk about a strong acid, we're saying it completely goes to the products, almost completely goes to the products. So really, at the end, in the solution, there's not going to be any HA left. All of it is going to dissociate into H3O plus and A minus. It lies so far to the right on equilibrium that we say it completely dissociates. On the other hand, a weak acid, so we'll use the same symbol, the HA, a weak acid only partially dissociates in the solution. So if we look at this little situation right here where H is going to donate H pluses to water to once again make H3O plus and A minus. So same general setup, they're both acids, but in this case, not all of the HAs are going to donate their protons over to water. Only part of them will. So what that means is at equilibrium there's going to be HA, there's going to be H3O plus, and there's going to be A minus. And naturally there's going to be water as well, but we don't consider it an equilibrium. So all three of those players will be in the situation with a weak acid, whereas with a strong acid, the only thing that's going to be in the equilibrium is going to be H3O plus and A minus. None of that. Where this makes a difference then, so if we go to a blank screen and we take a look at two acids, so HCl, which is a strong acid, when you put it in water, it completely dissociates into H plus and Cl minus. There is no HCl left in that jug, no HCl as a whole left in the jug. What that means then is if we go and we look at the jug and it says, hey, in this jug there is 0.5 molar HCl. Really, there's no HCl in there. What there is H plus and Cl minuses. So what we can derive from that then is the concentration of H plus in that jug is going to be 0.5 molar. The concentration of Cl minus will be 0.5 molar as well, but we're not concerned with that. What we'll use the H plus for then is for pH calculations later on down the road. But really there's not any HCl left in that jug. Everything's broken apart. On the other hand, if we talk about a weak acid, so weak acid like vinegar, acetic acid, CH3, COOH, and in this case it dissociates into acetate, which is CH3COO minus, and that hydrogen ion. That's what makes it an acid. Oops, sorry. Well, okay, that's a plus right there. So when this dissociates, what actually happens then is it sets up equilibrium. So there's going to be some of that as a whole left, there's going to be the acetate, and there's going to be H plus left in the solution. So not all of this guy right here is going to break apart into the ions. Part of it will be left as a whole. So it's a weak electrolyte, we would say. What this means then is if we go to our jug of acetic acid in the pantry, and it says, hey, look at me, I'm 0.5 molar. And if we wanted to figure out what the H plus concentration is so we can know what the pH is, well, we don't know that directly. There's not really a way that we can look at the jug and say, okay, so the concentration of H plus is going to be this. We have to do some more calculations. Since it is equilibrium, those calculations that we're going to end up doing are going to be, you got it, equilibrium calculations. Okay, but we'll get to those calculations later. Right now, let's just talk about acid strength and base strength, what makes them weak and strong, and how we would recognize something that's weak or strong. All right, so here's the good news with recognizing strong acids. All you need to do is memorize them. So there's 6 strong acids really the way you're going to want to recognize those is by just remembering what they are. So it's not going to be necessarily anything you recognize by looking at a formula. You recognize it because you know what the strong acids are. So here it is, these 6 right there. Write them on a flashcard, get those memorized. You are going to need to know what those are. It makes a huge difference for pH calculations. It makes a huge difference for Ka later on down the road. For bases then, because strong base, kind of the same deal. Bases are a little bit more easy to remember. So remember that all bases have that OH minus in them. Hang on 1 second. So all bases have that OH minus in them. The hydroxide, that's what makes them a base. And the strong bases will be one that have the hydroxides attached to a group 1 metal, and we just consider it all the way down to cesium because francium doesn't really do much. All of them down to cesium. Then if we actually trace that over to barium, up through strontium, and through calcium and back, we make a nice little B. B stands for base because those would be the strong bases. So if you have one of those 8 attached to the hydroxide, you consider that a strong base. So like LiOH would be a strong base. Calcium hydroxide would be a strong base. Just one of those 8. All right, so when we're talking about strong acids, something to know is that strong acids will always have a very weak conjugate base. So it's kind of that Jekyll and Hyde type thing. If you've got a really strong acid, its conjugate base is going to be really weak. On the other hand, if you have a really weak acid, its conjugate base is going to be really strong. So its alter ego is always the opposite of whatever it is. And then if you've got kind of a mid-range strength for an acid, its conjugate is going to be mid-range as well. So it's kind of a spectrum, and just when it meets in the middle, it's still in the middle. If we take a look at this in a slide, so HCl, let's get a pen we can see. HCl, if we put it with water so that we can see the interaction. So HCl is going to be an acid, so it's going to donate a proton over to water. It's the Bronsted-Lowry thing. And that's going to create H3O plus and Cl minus. So in this case, HCl is a strong acid, which means this is going to go completely to the right. So it's going to go lie really, really far towards the product side. But if we're talking here about acid strength, so HCl, since it is a strong acid, that means its conjugate base, which would be Cl minus, is going to be a very, very weak conjugate base. Which means that even though one might say H3O plus can donate a proton back to Cl minus is such a weak base that it can't really even pull that proton away from the hydronium ion. So it's not strong enough to get a proton donated to it. That's what makes it a really, really weak conjugate base. On the other hand, if we take a look once more at that acetic acid, so CH3COOH plus water, and that sets up equilibrium. The acetic acid donates the proton to water, so once again we get the H3O plus and CH3COO minus. Now, in this case, when we take a look at this, so the acetic acid donates the proton over to water, and then when we come over to this side, since CH3COOH, since this is a weak acid, it means that its conjugate base, which is that guy right there, is going to be a strong conjugate base, which means it can actually pull the protons away from H3O plus, thus forming it back into what it started as. And so this reaction can go backwards then as well. So this is a strong enough base to where it can force the protons to be donated to it, and it can drive the reaction back towards the left. So we have a weak acid with a strong conjugate base. Now if we think of this system kind of as being at equilibrium, so that we have all of the playas present, which means that in this system at equilibrium there's going to be that guy, there's going to be that guy, but it's a liquid. We're going to have hydroniums, and we're going to have acetate. So all 4 of those are in there. That means that there's 2 guys who are going to want to try and get protons. the waters are going to try and get protons like that, and the acetates are going to try and get protons. So we would say that these two right here are both competing for protons. Since this is a strong conjugate base, and this is just a regular base, that means that CH3COO- can actually outcompete the water for protons. And so it can take protons from both of these, essentially, and it will end up getting all the protons. So the equilibrium would lie farther to the left than to the right. Okay, so a strong base, that means it's going to drive the equilibrium back towards the left. Did I say right? I meant left. Towards the left, and we end up with a higher concentration of reactants than products. Okay, here's just a visual that shows that same idea. So when we go up this chart of acids, this list of acids, the strength goes up. And then all of the ones over on the other sides, those would be the conjugate base. So the conjugate base of Cl- would be a very, very weak conjugate base. It's at the bottom of this arrow. So the highest of all of these conjugate bases would be CH3-, which would be the conjugate of the weakest of the acids. And the strongest acid has the weakest conjugate base. All right, so we kind of talked about this earlier. In this case, HBr is donating its proton over to H+. And with this system right here, the two guys that are going to be competing for those protons would be water and Br-. But in this case, Br-, we said that since HBr is a strong acid, that means that Br- is a weak conjugate base. And that would also be a base. And so since Br- is competing for those protons as well, but it is too weak to take them from water, to outcompete water for them. So water is going to win, it's the stronger base, and so it's going to win most of the time, and the reaction goes almost totally to completion. If we take a look at a similar concept for a weak acid then, the weak acid we're looking at here then is ammonium. So ammonium NH4+, and H3O+, that would be the acid and conjugate acid. H2O would be our base, and NH3 would be our conjugate base. So since this is a weak acid, its conjugate base is going to be strong. And there's two fellas here that want the protons. It's going to be the water over on this side and the NH3, the conjugate base on this side and the base on this side. Since this is a weak acid, that means that this is going to be a strong conjugate base, which means it's going to have a higher pull for the protons than the water on this side does. So even though we draw the reaction like this, it doesn't actually go all the way to products, and so the concentration here is actually going to be higher on the left-hand side, so it's going to drive the equilibrium to the left. So the concentration of the reactants would be higher than the concentration of the products, and that's because the NH3, the ammonia, can outcompete the water for the protons. Okay, the last topic on acid strength would be the carboxylic acids. So if you look at this molecule right here, your first thought might be, hey, there's a base because it's got an OH on it. It has an OH, but it does not have an OH-. That is an oxygen covalently bonded to a carbon, which is covalently bonded to a hydrogen. So it is not going to break off into an OH-. And the OH- is key for making it a base. Instead, what we have here is that bond right there can get severed, and so we would have the H+ being formed in the solution. So a carboxylic acid you recognize because they're usually denoted as COOH attached to something or other, or CO2H. In this case, so you're going to see this little R term. R just means something, some kind of carbon chain. It can be anything attached to it. If we take a look then at two carboxylic acids, let's see, how about we do CH3, C2, double bonded to O, single bonded to O, single bonded to H. So this right here is going to be acetic acid. That's the CH3COOH that I've been talking about a lot, just drawn on its actual structural formula. So this guy is going to, at equilibrium, kind of ditch that bond right there, and so we'd end up with the H plus and the CH3COO minus. So let's compare two carboxylic acids real quick and talk about the strength. So CH3CO. Okay, let's try that again. If we compare two organic acids or carboxylic acids, first one we'll do is just acetic acid again. So CH3 blast. That's, yeah, CH3 to C double bonded to O to OH, so that's acetic acid. And let's compare that in turn to trifluoroacetic acid, which is CF3 to C double bonded to O to H. Okay, so if you compare those two structures, they're actually really, really similar. They have the same number of carbons, same number of oxygens and hydrogens. The only difference between these two is the acetic acid has an H3 right there, and this has an F3 right there. So make note real quick that on CH3, those H's are covalently bonded to carbon, and they're not going anywhere. The hydrogen that comes away to make it an acid is this hydrogen right here, the one that's attached to the oxygen. Same thing with over on this one. The H right there is the one that slips off to make it acidic. So if we wanted to talk about acid strength with these two, we would look at the R group, which is, this side right over here. So that would be our R group. That would be the R group before. The more electronegative the R group, the stronger the acid. So once again, the more electronegative the R group, the stronger the acid. And that's because if we think of electronegativity, it's the pull for electrons towards a certain element. So for acetic acid, it's going to have a very, very weak pull over on this group for those electrons, because that's not a very electronegative side right there, the carbon and the hydrogens. Hydrogen is extremely weak, which means that the bond right there is going to be pretty strong. On the other hand, if we look at carbon trifluoride right here, remember fluorine is the most electronegative element, which means it's going to have an extremely strong pull for those electrons, which means all of the electron density is going to move over towards this side, and little hydrogen, hey, what about me? It's going to lose its bond to oxygen pretty easily and come off as H+. So it will be forgotten, slip off, and that will make this a very strong acid. And remember, by strong, we mean dissociation. So it will dissociate a lot into H+, and then CF3COO-, as opposed to this one right here, where there's not a very strong pull for the electrons anywhere on this element. They'll stay pretty evenly central, and so this H+ isn't really going to slip off very often. It's going to stay happily attached.